Good day, everyone, and welcome. Today, we are going to explore one of the most important and fundamental laws in all of electrical engineering, Ohm's law. Now, do not let the simplicity of its name fool you. This one equation, V equals IR, is the backbone of everything you will analyze in circuit theory, from a simple resistor in your lab kit to the complex power grids that light up cities. By the end of this lecture, you will not only know the formula, you will truly understand what it means. Let us begin. Before we talk about Ohm's law, we need to understand what resistance actually is. Imagine you were trying to walk through a crowded market street on a Sunday afternoon. You can move, but the crowd is slowing you down, pushing back against you. That opposition to your movement, that is exactly what resistance is for electric current. Formally, resistance is the capacity of a material to impede the flow of electric charge. Every material, copper wire, carbon, even your own body, offers some degree of resistance to current. Now, in your circuits, the component that models this behavior is called a resistor. It is an ideal basic circuit element, and it is mathematically described using the relationship between its voltage and its current. And the second concept on this slide, Ohm's law, is precisely that relationship. Named after the German physicist Georg Simon Ohm, who established its validity in the early 19th century, Ohm's law tells us the voltage across a resistance is directly proportional to the current flowing through it. The constant of proportionality is the resistance itself, measured in ohms. This is the golden triangle of circuit analysis: voltage, current, and resistance. Learn these three and their relationship, and you have unlocked the gateway to all of circuit theory.
Let us now look at Ohm's law mathematically. The statement is beautifully simple. The voltage versus across a resistor equals the current I flowing through it multiplied by its resistance R. So we write V equals I times R. And on the slide, you can see the three equivalent forms: V equals I times R to find voltage, I equals V divided by R to find current, and R equals V divided by I to find resistance. You will use all three in your numerical problems. Memorize them, but more importantly, understand what each one is saying. Now, let us note an important definition. The resistance is said to be 1 ohm when 1 ampere of current flows through it, and the voltage measured across it is exactly 1 volt. That is the definition of 1 ohm. Simple and precise. Also, a quick but important point. The reciprocal of resistance is called conductance, denoted by the letter G. Its unit is the MHO, sometimes written as the upside-down omega symbol. Conductance tells you how easily current can flow. The higher the conductance, the lower the resistance. Now, on the left side of the slide, we have the assumptions and applicability of Ohm's law. Keep these in mind. First, in this lecture, resistance R is assumed to be constant. In reality, resistance does vary with temperature, pressure, and material conditions. But for now, we treat it as a fixed value. Second, Ohm's law applies to both DC, direct current, and AC, alternating current circuits. This makes it extremely versatile. Third, by convention, current enters the positive terminal of a resistor and leaves from the negative terminal. This is the passive sign convention, and you will see it used everywhere. Fourth, current always flows from higher voltage to lower voltage. Think of water flowing downhill. Electricity behaves the same way. It always seeks the lower energy level. And now, two very important special cases on the right side. If R equals 0, that is a short circuit, a wire with no resistance. The voltage across it is 0 even if current is flowing through it. If R equals infinity, that is an open circuit. No current can flow at all, no matter how much voltage you apply. These two extremes are your boundary conditions, and you will encounter them constantly in your analysis.
Now, let us talk about what kind of resistor we are actually assuming when we apply Ohm's law. We call it a linear resistor. A linear resistor is one that obeys Ohm's law. It has a constant resistance value regardless of the voltage applied or the current flowing. Here is the key characteristic. If you plot the current I on the horizontal axis against the voltage V on the vertical axis, what we call the IV characteristic, you get a perfectly straight line passing through the origin. Why through the origin? Because when V is 0, I is 0. No voltage means no driving force for the current. The slope of this straight line is exactly R. The steeper the line, the higher the resistance, and the more difficult for current to flow. For this entire lecture, and for most of your first year, we will assume all resistors are linear. This is a reasonable and very useful simplification that allows us to build powerful tools for circuit analysis. Now, nature is not always so cooperative. Not all components obey Ohm's law, and that brings us to nonlinear resistors. A nonlinear resistor is one where the resistance changes depending on the amount of current flowing through it. So R is not constant. It keeps changing. If you plot the IV characteristic for a nonlinear resistor, you do not get a straight line. The curve bends. It could be exponential. It could saturate. It could have all kinds of shapes. Two very common examples of nonlinear devices are the incandescent light bulb. As the filament heats up, its resistance increases dramatically. A cold bulb has a very different resistance from a glowing hot one. And the diode, one of the most important components in electronics. A diode allows current to flow freely in one direction, but almost completely blocks it in the other. Its IV curve is highly nonlinear, an exponential relationship. We will study nonlinear components in detail in later semesters. For now, just know they exist and recognize that Ohm's law alone cannot describe them.
Theory is best understood through practice. So let us apply Ohm's law right now with a real-life problem. Consider a toaster. The essential component inside a toaster is a resistive heating element which converts electrical energy into heat energy which toasts your bread. Engineers call this joule heating. Here is the problem. Given resistance R is equal to 60 ohms and supply voltage V is equal to 230 volts, which is the standard mains voltage here in India. Find the current drawn by the toaster. Let us solve this using Ohm's law. V is equal to I times R. Rearranging, I is equal to V divided by R. So I is equal to 230 divided by 60. That gives us I equals approximately 3.833 amperes. So your toaster draws close to 4 amperes of current from the mains. Now you understand why a toaster has a thick power cord. Thin wires cannot safely carry that much current. This is exactly how engineers size electrical components using Ohm's law as the starting point. Simple, powerful, practical.
Excellent. Now let us take on a slightly more involved problem, one that brings in conductance and power as well. Looking at the circuit diagram on this slide, we have a voltage source of 30 volts connected to a resistor of 5,000 ohms, which is 5 kiloohms. We are asked to find three things. 1, the current I, 2, the conductance G, 3, the power P. Let us solve them one by one. First, the current. Using Ohm's law, I equals V divided by R. I equals 30 divided by 5,000. I equals 6 milliamperes. We write this as 6 milliamperes. Next, the conductance. Conductance G equals 1 divided by R. G equals 1 divided by 5,000. G equals 0.2 millisiemens, written as 0.2 ms. And finally, the power. Power P equals V times I. P equals 30 volts multiplied by 0.006 amperes. P equals 180 milliwatts, written as 180 MW. So from a single voltage and resistance, we have found the current, the conductance, and the power consumed by the resistor.
3 results, 1 fundamental law. Remember this workflow. Ohm's law first, then derive everything else. This is your standard approach for all circuit problems going forward. Thank you for your attention today. We have covered the foundation, resistance, Ohm's law, linear versus nonlinear resistors, and 2 practical numerical problems.